That'll do. I'll do it in there anyway. So I'm just going to talk about a little bit about the sky in April and what's coming up, and a customary look at the sun, because the sun is getting very, very interesting at the minute. Particularly if I just bring my laser out. This spot here, 3256, near the edge of things. There's quite a lot else going on as well, particularly at the top here. But that one has actually gone bang in the middle of the night. So with an X1.2 class flare, there you can see it exploding there. And although that's not obviously pointed straight at us, apparently it's big and bright enough that we will get something off it. And also, this coronal hole here is sending out some solar winds towards us to arrive at the weekend. So if we get any clarity at all, I'm afraid the forecast is of course terrible, but aurora potential for Friday and Saturday night. And that's coming along quite nicely now, because that was last week's effort. I just had a little walk down to the beach. I was very, very lucky actually that I've got a friend at work who actually came out to Ballygally hoping to see the aurora, and she said, we stayed till just after 10 and there was nothing doing, so we went home. I insisted on watching The Apprentice final because I'm a fan, and went down about 10:15 and it was just kicking off, so they weren't totally happy. That's my little space weather gallery. That's quite wide and quite big actually. That is a 4-shot panoramic photo from the beach at Ballygally, and you can sort of get the idea of how wide it is. It's probably, I would say it's about 100 degrees across and 30 degrees high, something like that you're looking at there, because this is up the Antrim coast here, and that there is the light pollution of Glasgow, believe it or not, which is some 80 miles away. It's amazing just how far that goes, but got a few nice beams there, and it is quite good. I'm sure this massive cloud here just wouldn't go away. And that's, it would have been a lot better had it done so. But that wasn't bad. That was the 23rd, 24th of March. So we're hoping that these things will come along a bit more.
Paul, how much of that was camera and how much was visual?
Oh, I mean, I could see colour in it. I could see green colour in it. I mean, I would say that one of the things I'm quite aware of is the structure. And I tend to sort of move the camera around to try and capture bits of structure that I can see going on. The colour, no, it's not that intense at all. The colour to the naked eye is a very faint pastel green. You can see that it's more than a white fog, which is the first level that you see. So there's a little bit of green there. The red, shows only as a whitish fog. The eye is much more sensitive to green than it is to red, and at those light levels it's not terribly sensitive to colour at all, really. So it's these are all 10-second exposures, and the eye doesn't do 10-second exposures. It's that simple, really. The eye is a continuous sensor, but it collects an amount of light that is similar to a shutter speed of about a 30th of a second in a camera, and ISO 1600, which actually these coincidentally are as well. So yeah, it's a lot of that is camera, but actually it wasn't invisible. I did see it. So somewhere in between, I've seen some real serious over-processing going on actually. But I mean, some people just get into Lightroom and they push all the sliders up. They go, oh yeah, vibrance, all of that, and saturation, plenty of that too. I haven't done that, but the camera does pick up more than I saw. I've shown you this before, I think, but it is very important, because the original supposition was that solar cycle 25 was going to be much like 24, which is to say not all that great really compared to the 3 before it, which were even bigger. You can see these actually here. This is 25 prediction. That was 24. 23, 22 and 21 in the decades before, they were actually quite big. My father told me that he saw an aurora in 1949 in that thing there in the north of England. But what's happening with cycle 25 actually is that we're taking readings of what's actually happening, and that's way ahead of really what was predicted. So we're doing quite well here. Hopefully in years to come we'll see plenty. So keep an eye to the north when the opportunity arises, which is really when the clouds go away. So your moon phases for the month of April, and we're sort of coming to spoil things now. If you were thinking of doing a Messier marathon, I think you've probably missed your opportunity because the moon is now coming up again, and by the weekend it's be waxing gibbous. It's full on the 6th of April, so just over a week's time, and new again on the 20th. But actually, really once you've gone past the full moon, you do get some moonless observing time in the evening before it comes up. So if you think that a last quarter moon will come up sometime around midnight, so you've got all the time before that to get some moonless observing in. It doesn't have to be new. And so that's your moon phases. Planets. Now then, if you read the newspapers, you'll be under the impression that all you have to do is look out your window any evening this week and you'll see 5 planets. And this isn't really true. You'll probably see 2. In fact, 2 are really easy. I didn't get Mars in on this, but Mars is just up beyond Taurus there. But Jupiter is more or less lost to us completely. It's too close to the Sun to be easily visible, if at all. And if you were going to look for it, you'd need a perfect western horizon that's there. Mercury is a bit better. In fact, I'll show you Mercury again in a minute, but this is probably one of the best times of year to see Mercury in the evening, but it's still pretty low. It's reckoned that less than 1% of the world's population have ever seen Mercury, which is rather strange, you might think, considering it can be brighter than Sirius. But it's always very close to the horizon, either in the morning or in the evening. So not that many people have actually seen Mercury. You have to know where it is, what you're looking for. And even though it can be quite bright, you won't necessarily see it easily. Venus is really easy, of course, because it's incredibly bright. And it is beginning to see a little bit of a phase as well. It is notably through a telescope now, not round as it comes towards us, coming around the Sun. And the 5th planet they tell you that you can see just by stepping out your back door is actually quite near Venus. It's Uranus, but its magnitude 5.8. A small number of people can see it naked eye, because it is, but I never have, and so I'm prepared to take the word of those who have. I'm showing Mercury there. I forget what date I set this for. Let's have a look. I set this for the 4th of April, just arbitrarily. 10 to 9 in the evening. There's still quite a lot of light in the sky now. We've got it summertime. But Mercury is actually sort of headed up and then down the other side again. And over the first 2 weeks of April, you get reasonably good views of Mercury. If you never have seen Mercury, it's a good chance to have a go at it. But you will need a good western horizon to see it. Okay. That's all I have to say there. I was just going to talk about planets because I talked about all the realm of galaxies and all that last time. So stay safe and keep looking up.
Oh, that's great. Happy to see.
And the background to that. And then I'll give you a wee look at where we're going next and what's going to happen after this. So, SALT is the Southern African Large Telescope. It's not the South African Large Telescope, it's the Southern African Large Telescope. And it's housed in that dome on the right of the picture. This is, and I had a look at this picture and I thought, that's interesting. Sunrise that far around, so this must be taken in the summertime, because the sun is way round to the south. That road runs almost north-south on axis on the mountaintop. So you may have seen pictures of the mountaintop before. You may have seen this aerial view of the mountaintop. I have a long history association with this observatory. It's 40 years ago this year that I made my first trip there to observe with, now I'm going to see if I can remember how the laser pointer on this works. Ooh, no, that's not what I meant to do. And I don't suppose I've got a cursor. Here we go. So this is SALT. This is the 30-inch telescope. This is the 20-inch telescope, and that's where I started. I was telling Terry about my first observations of Omega Cen 40 years ago this year from this telescope. And then this is the 1 meter and the 1.9 meter, and I've observed with all of those as well. So this is in the middle of the Karoo in Cape Province in South Africa, and this is the mirror mosaic of SALT. And you must be thinking, why is it sort of all sorts of different colours? Why are there dark hexagons and grey hexagons and yellow hexagons? Well, actually, you're looking at dust. Each hexagon is about a meter across, and each one is cleaned and re-illuminized separately. And so there's a cycle, a rotation cycle of the mirror is disassembled, one comes off and goes for re-illuminizing, and another one goes back in its place. And so the darker ones are the clean ones, and the other ones have dust sitting on the top of them. And just because of the angle you're looking at them, they look really, really mucky. If you're looking down on it from above, it wouldn't look quite so bad. Now, SALT is a very interesting telescope. It's an 11 meter, in principle it's 11 meters across, but the optics actually only sees 10 meters at a time. And you think, oh, what's going on? How does that work? And this next diagram gives you a little bit of or tries to explain what's. I can turn it around there. I can come around and point how the telescope works. It's got a fixed altitude mounting, which means it will only point at a certain angle to the horizon, but it can rotate around at that angle. So it can see basically a ring or a donut shape on the sky. And if you can imagine what's happening to stars as they come across the sky, most of the stars within between the north end of the donut and the south end of the donut are going to cross sometime during the night. They're going to cross that donut. So in principle, you can see a star every night that it's on our side of the sun, but only for a short time, and then it maybe crosses into the middle of the donut or passes beyond it. And so we rotate the telescope, and the star comes across. And the second thing that's special about it is that once you've moved the main telescope, you don't want to be trying to rotate that during the course of your exposure. What happens is this assembly on the top, which is where you'd call it the secondary mirror on another telescope, but it's actually the main acquisition optics are sitting up here, and they're sitting on a tracker, and that tracker moves, that whole assembly, which is several tons in weight, moves along that track. And the track can be rotated around the ring at the top of the telescope, and then the tracker can move to follow the image of the of your object, which is reflected from the primary telescope. And as the star moves across the sky, that focused image also moves across, and the tracker follows it without moving the telescope. So pretty neat. And the reason for doing this is it's about a fifth the price to build of a fully steerable telescope. So this is a cheap way of building a big telescope. There's some other things to note in this diagram of the telescope. We've got our main mirror here, we've got the tracker, we've got the secondary optics, and sitting up here, this is an expansion of the secondary, of the payload as they call it. So there's a complicated lens assembly here which corrects the image for all the distortions that a spherical cross-section lens mirror gives you. There's an imaging camera over here, and RSS is the Robert Stobie spectrograph. So this is the workhorse low-resolution spectrograph. There is another spectrograph which is down in the basement, somewhere down here, which is the high-resolution spectrograph. I also use that, but what I'm going to be talking about tonight are observations made with the Robert Stobie spectrograph. And here is a picture of the Robert Stobie spectrograph. Now, I know that probably won't mean a huge amount, but I wanted just to show a picture of this, because I'm going to be talking about spectra rather than images, and you must be interested in, we're interested in how these are generated. The light comes in from the telescope through that secondary optics and this cone here, and it comes into the focal plane of the telescope here, and there's a magazine of different bits and pieces that can be slotted in. There's another set of magazine of bits and pieces up here which can be slotted in, and there's a flat mirror, and somewhere in here we're going to find some gratings to disperse the spectrum and spread the light out as a rainbow, and somewhere inside here is the camera that records the spectrum. So this is a huge beast. It's not quite as big as a car, but it's not far off it, and it's sitting way up in the top of the telescope dome. So that's the instrument that we've been working with, and next I want to talk about hot subdwarfs. Now, hot subdwarfs are stars. To illustrate a little bit what they might look like, this is the center of a globular cluster, and you see stars of all sorts of colors. We see bright yellow stars, we see faint yellowish stars, and occasionally we see the odd bright blue star. This is not bright enough to be a main sequence star. In fact, this population of stars being in a globular cluster is so old that we don't have blue main sequence stars. So this is, it's actually less luminous than another main sequence star. So we call it, we can draw a diagram of brightness against color of stars in the sky, and this is these are two diagrams, color magnitude diagrams we call them. On this one is one of the globular cluster that we've just seen a picture of, and we have the bright yellow stars, bright red stars up here, and most of the stars sitting down here. But over here we have the blue stars, and this is a corrected color magnitude diagram made with the Gaia, the astrometric survey telescope, which is revolutionizing astronomy at the moment. And on this color magnitude diagram, we see the main sequence of stars, we see the giant branch, and we see the red giants up here, and we see the white dwarfs, of which there are many of them. And then there's a group of stars here. Now, I came across this quotation on Stack Exchange some time ago, and the question put on Stack Exchange was, what is this clump of hot and dim stars? To which a user by the name of HDE225648, or something like that, you know, users on Stack Exchange have odd names, 226868. My best guess is that these are subdwarfs. And in fact, HDE226868 turns out to be absolutely right. But what is a subdwarf? Well, the correct answer is that it's a star that is sitting in that clump down here. It's a blue star, which is subluminous, and it's not a white dwarf. Some of them, in fact many of them, are believed to have the following structure. They're believed to be stars of about half a solar mass that are primarily helium. They're the remnants of a red giant star. A red giant star that's had all of its surface hydrogen ripped away, and it started to burn helium in the core. Now, usually the surfaces are very rich in hydrogen, and not a lot else to be seen. Often these stars are double stars, and they've got various companions, and that's really interesting because it means nature has more than one way of making these. But nature can't make them as single stars, but it can make them as in double star systems, and they often pulsate as well. So we know quite a lot about most hot subdwarfs, and there's a lot of interesting physics goes on inside them because they're very stable, because they're very bright and hot, and the physics of diffusion and radiation happen inside them. Really interesting from that point of view. But I don't want to talk about, well, you know I'm not going to talk about these. What I would like to be talking about, really, are some of the peculiar subdwarfs, because sometimes stars in that clump are really strange. They've got no hydrogen. They're different. Some of them have really exotic chemistries. There's one we know of which has lead, which is 1 million times more abundant than it should be. Zirconium in another star is 10,000 times more abundant than it should be. And there's some other weirdos. There are lots of other weirdos in there, and it's great fun exploring these. And that's what we've been doing as our salt survey of helium-rich subdwarfs. And that's where this talk really starts. And I'm naming some of my collaborators, Brent Nijalsky and Tumaleng Monaghan, are very important, both from the contributions scientifically, but because they've been part of the South African side. And that's unlocked for me. Armagh is a member of the UK Salt Consortium, and we buy about 12 to 15 hours of telescope time per year. By collaborating with the South Africans, I've been able to multiply that by at least 5, if not more. We'll look at that, and that's been the key to this. And there's some other great people on that list. So, what are we going to do? How do we go about trawling through, looking for these stars and understanding them? And I'm going to just take us a little bit back to some basic astronomy, and to remind ourselves of spectral classification, and show you a range of spectra of different stars. And you'll see the one at the top has most of the light in the blue, and the one at the bottom has most of the light in the red, and the ones in the middle have the light in the middle. And, well, if you were an early astronomer, you would probably be collecting spectra and trying to organize and say, oh, this star's got a spectrum like that one, and this star's different, and this one's like the other one, and you'd want to arrange them. And that's exactly how spectral classification works. You are making a phenomenological sorting of these things. And we attach labels to them. And the one at the top is now known as an O-type spectrum, and the one at the bottom is an M-type spectrum. And you'll be familiar with the sequence OBAFGKM. And we also now know that we can associate temperatures with those stars. 50,000 Kelvin at the top and 3,500 Kelvin at the bottom. And the Sun is a G-type star with a temperature of around 6,000 degrees. So there's our phenomena. We've got our hot stars, which are blue, our cool stars, which are red, and sitting within those colors are dark bands. And those dark bands are the absorption lines that come from different elements. And you can see, I've highlighted there the principal hydrogen lines. And the hydrogen lines become much more prominent in the hotter stars. They're less obvious in cool stars, mainly because the hydrogen is all neutral and some of it's molecular, and it doesn't absorb so much light at those temperatures. Now, as I've said, spectral classification is about organizing the appearance of stars' spectra and using that organization and that knowledge of what the spectrum looks like to recognize that something's normal or familiar or really unusual. And what we've been doing with the SALT survey has been to look at stars that we think may be helium-rich subdwarfs, in other words, of interest to my particular for my particular questions, and organize them. And I've just given a picture of some of the spectra that we've observed with SALT. These are all helium-rich subdwarfs, all very similar. They actually cover a very narrow range of temperature, and these sorts of diagnostics that we use to make decisions. And these would be pairs of lines. We'd look at a helium-2 line and a helium-1 line to estimate temperature, or we'd look at the width of a line to estimate how actually what it tells us is how dense the atmosphere of the star is, and that tells us something about the gravity, the surface gravity of the star, just as the density of the atmosphere on Earth is actually a consequence of the mass and the radius of the Earth. We also compare the helium lines with the hydrogen lines to tell us what the chemistry is. Is it a helium-rich star or a hydrogen-rich star? And this process can be easily automated. It's model independent and tells us all sorts of things, and it can give us a picture of stars across a parameter space. And the ones along the top are all extremely helium-rich stars, and the ones at the bottom are hydrogen-rich. And we see there's a bridge in between. And I won't go in say very much more about that. We can go on, we can use that data to tell us, the same data, the spectra, to tell us about the temperatures and gravities and make measurements of hydrogen and helium ratios. And we can find patterns of all sorts of different classes of subdwarfs, and we see the temperatures run from around 20,000 Kelvin to 60,000 Kelvin. We have stars that have roughly solar abundance, and these are actually helium-rich for subdwarfs, because most subdwarfs are helium-poor, but most of them are these things are very helium-rich, up to 100 times more helium than there is hydrogen. Lots of interesting things in there, and we're following up on individual stars, and but as things turn out, the wider you cast your net, sometimes there are stars in that collection that aren't what you were looking for. They don't seem to fit. Not everything is a hot subdwarf. And I collected the things that weren't hot subdwarfs into this diagram and looked at them and said, okay, well these are white dwarfs. They've got lines that are very wide, which means that the gravity is very high, which means that the radius is very small. These are white dwarfs. And well, DB white dwarfs, TA white dwarfs. There's millions. You saw on that Gaia diagram there's lots and lots of white dwarfs. We're not interested in white dwarfs. So it's on the point of saying, right, we'll just chuck this lot out. And then I had another look at it. And I don't know if you can see anything, but down here there are some lines that have a little spike in the middle of them. Oh, that's interesting. What's that? Why have we got what's known as an emission line? So if you have a bright light and a gas, a hot gas between you and the bright light, then the light that comes through the gas can be absorbed in an absorption line. It's blocked out. So normally we would expect to see an absorption line. An emission line happens when you've got a hot gas without a light behind it, and the reverse happens, the gas is emitting. It's actually doing both at the same time, but in this case you haven't got the light behind, you see an emission line. Normally we just, when we look at stars, the light from stars, we see absorption lines. But sometimes we see these emission lines. And it's usually a sign that the star is very hot. So I sent this spectrum to my colleague Klaus Werner, who's a guy I have known for a long time, shared an office with him in the 1980s, and stayed good friends since. He said, oh yeah, that's very interesting. I think that might be a certain type of star, and he thought it might be a dear white dwarf or something. And he has the skill, he has the models to measure the temperatures of these stars. And he did that, and he said, oh, at a quick glance, that's got a surface temperature of 130,000 Kelvin. Now, 130,000 wasn't on my graph. I had a graph that went up to 60,000. My models only went up to 60,000. 130,000, that's toasty. So rather than rejecting these, I thought, well, maybe this is bycatch. Maybe there's something really interesting to look at here. And so I'm now going to talk a little bit more about the super hot zombie stars and try to explain why we call them zombie stars. So in that first diagram, I'd seen three objects with emission lines. I went back through the data set, and well, there was one star we knew about, but we knew that it had emission lines. We knew it was in the sample because it was selected for that. It's the central star of a planetary nebula. We knew it to be very hot, and it's very famous, and it's called NGC 246. We found 8 other stars that were of definite interest in this. And here's the plot. Go over and draw attention to them. You see this line here. This is the emission line from ionized helium 4686. And that's our key indicator. But we're also seeing things from nitrogen 5 over here, and there's a group of lines down here from carbon 4. That's triply ionized carbon, quadruply ionized nitrogen. These have to come, these ions have to be very hot, or the plasma has to be very hot for us to see such emission lines. Klaus Werner now did some more careful analysis, and I'll just show I'll just really mention what he did. He uses a thing called the Tübingen model atmosphere package, and the specialized treatment for temperatures greater than 50,000 Kelvin. And it's good enough for us to be able to measure hydrogen, helium, carbon, nitrogen, the surface temperature and the surface gravity. Now, most of that blue squiggly stuff is noise. These are faint stars. For the resolution we were working at with a 10-meter class telescope, and we're still struggling to get good sounds and noise. The next slide is going to give you a summary of what we found. Look at the table at the top and look at the temperature-headed T effective. And you'll see numbers ranging from 110,000 all the way up to 180,000. All of these stars are well over 100,000 Kelvin, and 180,000 is, it's hotter than you can do with your kettle. But you'll also see that we've given a number of different classifications to these stars. We call one is a DO, and that's a DO white dwarf. 3 are OAG stars, 2 are OH stars, and 2 are PG1159 stars. And you must be thinking, this guy's absolutely off his trolley. Why has he got all this strange? I've never heard of any of these types of star in my life before. And that's true. Just out of interest, has anybody heard of any, apart from the DO, or maybe nobody's heard of the DO, has anybody heard of any of those before? That's what I was worried about. Well, but that's also what I assumed. So I'm going to try to unwrap that a little bit. And I'm going to talk about what happens to a star towards the end of its life. I hope that most of you know that a star, well, unless a star ends its life as a supernova, it usually will end its life as a white dwarf. Is that okay? We're happy with that. Good, good. And a white dwarf is a very faint, sort of dead, very dense object. So that's where we're going. And where we're going to start off is with the evolution of a normal star as a single star, and it goes through its main sequence hydrogen burning phases, and it goes through its core helium burning phases, and it ends up in what is known as an asymptotic giant branch star, which is a star that has a carbon-oxygen core, it has a helium layer around it, and then outside that it has a hydrogen layer. And its huge luminosity is it that one? That's well, it seems to. It's a bit of a whistle around.
Yeah, just kind of.
Okay. This huge star is maintained by the luminosity of the hydrogen burning at the base of its envelope. But that can't last forever, because although it's got fuel, it's burning through that fuel at a fantastic rate, and eventually there's none left, and the hydrogen shell starts to die away, and the star starts to shrink. And what happens when it starts to shrink is it doesn't go back down the asymptotic giant branch. We've gone, so far what we've done is we've gone up here and up here. It doesn't go back down here. It basically stays at the same luminosity, because the star is telling it, the structure of the star is telling it, I am this bright. I am 10,000 solar luminosities, and I am going to shine at this brightness. And the only way I'm going to carry on shining at this brightness is to convert all this energy I've got from being big into radiation by shrinking at this luminosity. And it does it like this. And the star evolves across, shrinks over towards here until it's nearly the size of a white dwarf. So young white dwarfs are up here, and old white dwarfs are down here. And what we're interested in is stuff that belts across here. And our first, the first two stars that we're going to look at are the OH stars, and we think that they are one of the stages that a star goes through as it's coming across this part of the diagram. Other stars, or some of these stars, can illuminate a planetary nebula. The planetary nebula is material that's been thrown off by this star when it's over here, throws the gas off, the star heats up, and then it ionizes that nebula of gas around it.
And what are the numbers, decreasing numbers from 9.1 on the main sequence as you go up the previous slide? 9.1 and then 8.3, 7.7 and so on. Is that the mass of the star as it loses mass?
Yes, that is.
Right.
Yes, that's correct. So in that particular model, yes, it starts off as 9 solar masses, ends up there at 6.4 solar masses, but it will throw off most of that nearly 6 solar masses as it goes up the AGB before it comes across.
Right.
So this is the observer's way of looking at the extreme left-hand end of that last figure, and all of these stars are OH stars. The ones with which are filled in don't have a planetary nebula. The ones with circles around them do have a planetary nebula, and these stars have hydrogen, some hydrogen at least, on their surfaces. When we found these two stars were in this region, one colleague said, "Oh, I wonder if any of these have a planetary nebula around them." So we took another look, and we looked at some very deep imaging, and lo and behold, Brent Nijalski found this image down here, and you can see the grey region centered on our star. And of course, our spectrum was not just a spectrum of the star, it included the spectrum of the sky on both sides of the star. So this is the spectrum of the star along here, and this is the spectrum of the sky on either side. And you can see these extended emission lines, and these correspond to lines that you commonly see in a planetary nebula. They come from oxygen 3, helium, and hydrogen. And so what we've discovered is an OH star without a nebula and an OH star with a nebula. Anecdotally, somebody asked, well, what would you call the planetary nebula? Because the planetary nebula always have a name of some sort. So we asked, and I said, well, the convention would be, it wouldn't be Jeffery 1, no, but you could use the initials of the first two letters, the first three authors on the paper. So that's Jeffery, Werner, and Kilkenny 1. I think JeWeKi 1 sounds quite good. Okay, so something else can happen, and you might have noticed this on the last figure. Some stars get down here and turn the corner, and this is a plot of a similar evolution track. The star comes along here, comes down here, and then something happens. There's still enough hydrogen and enough helium on the outside of the star for the helium to reignite. It's not totally dead. It's a zombie star, yes. So that helium can reignite, and when that new energy source, it doesn't sort of switch on and shine through the layers above it. It forces the star to expand. And that means the star whips around, depending on the models, it comes around here, and it ends up coming right the way back over here to become a yellow supergiant again. We call this a very late thermal pulse. Some people call it a final flash, and it can happen very quickly. And we've observed stars that do this. Saccharide object, B4334 Sagittarius, did this in the 1990s. FG Sagitti did this and there's another one that did it in the early 20th century. And Sakurai's object took literally weeks to go from here to here. Phenomenal. And then, of course, it has this brief spell of shining, sort of a last gasp, and then that fuel was never going to last very long, and so the star shrinks again back in this direction, and starts to become a white dwarf. But in the process, what it's done is that the pulse has mixed up all the layers between the core and the surface. Hydrogen's now been dragged down, and carbon has been brought to the surface, and so the surface composition of the star is completely changed. And so by the time the star gets back to around here, it's got a helium-rich surface, and that's where we see it's also got carbon in it, and that's where we see the PG1159 stars. You remember I talked about the carbon emission lines. We see the carbon in these stars. Now the PG1159 stars are fantastic because they have these really processed surfaces. Most of them are mixtures of helium and a lot of carbon. There are one or two that are just carbon and oxygen with no helium. The ones that have just carbon and oxygen are really hot. We've not got complete record breakers in this class. The carbon and oxygen mixture ones are at 250,000 Kelvin. So even off this diagram. But these two are record breakers in another way. We saw these, and my colleague said, "Oh, that's the region where some of these stars are variable." And I have another good colleague, and he works in South Africa. Actually, he's retired in South Africa, but he still was about as active as any of us, and regularly goes to the telescope. And he was just about to go to the telescope, and he said, "Look, these are still visible. These are still in the sky. Are you interested?" Yeah. And he got these light curves. He observed both stars on 3 nights within the week, and you're probably a bit skeptical. It's a bit ratty, but you can probably see that it's going up and down. And when you do the Fourier transform, you can see there's definitely a period that persists. And in fact, these are what are known as GW Virginis pulsators. Now I said these are PG1159 stars. PG1159 minus 035 was one of the sexiest stars around when I was when I just finished my PhD. This star was hitting all of the headlines because it was obviously very hot, and it had this amazing light curve. Now this is a modern light curve that goes up and down and has lots of periods. And when things pulsate, you can learn a lot about their insides from using the science of astroseismology. So our two stars are like this. They're not as beautiful as this one, but J2137 is one of them, and it's the hottest GW Vir star in the sky. So that's one of our records. The next zombie stars I'm going to talk about start life. Well, they don't start life. You think they're going to end life like this, as white dwarfs. But you know that many stars are double stars. And if both stars end their lives, what have you got? You've got 2 white dwarfs in a double star system. And if you're lucky or unlucky, you find a double white dwarf system, which has a very short period orbit. And they do exist. And they've been observed with orbits less than 2 hours, sometimes as short as 30 minutes or less. Imagine 2 stars as half the mass of the sun, circling around each other in a few minutes. In fact, the size of the orbit is less than the size of our sun. In some cases, it's less than the size of Saturn. These are big beasts. what happens when you've got two stars, two heavy things orbiting one another? You generate gravitational waves. Basically you've got a gravitational dipole, it's rotating in space, and it's creating gravitational waves which move away. What happens if you take energy away from a binary system is the orbit loses energy and the two stars start to move together. What's going to happen? They're eventually going to collide. And then what will happen? Well, what happens next is a really important question, because if the total mass of the system is big enough, you can get a type 1a supernova. Type 1a supernova are all sorts of things that people get really excited about because they're standard candles and you can work out the scale of the universe from them. If they don't make supernova, then I'm interested because I think they'll make a helium star. They'll make a new star because what will happen is that one star will be accreted around the other one with fresh fuel. A star will be reborn, and what have we got? We've got a second type of zombie star, because that star can also be renewed. There's a wee cartoon of various outcomes. If we had a gravitational wave detector like LISA, so 10, 15 years time, when you're listening to me giving this talk, I'll be telling you about LISA and its observations of these. And gravitational, you've got an orbital period of thousands of seconds, and you've got the gravitational waves, and it becomes visible in LISA, and at some point the two stars merge together, spiraling, they merge together, and they could make a supernova, or they could make a helium star, here's an alcohol star, or they could make another type of star, depending on the initial conditions. So let's just suppose that we end up with an Alcorona Borealis star, and this is where I started many years ago, asking the question, what are the extreme helium stars? And we came to the conclusion about 20 years ago that, well, we eventually made the models that showed that becoming an extreme helium star was indeed a likely outcome. The suggestion had been made nearly 40 years ago by someone else. So what happens here is that our two stars merge, reignite, and again they become a yellow supergiant for a while. Same story. They spend time as a yellow supergiant, but all things come to an end. The star contracts, and these two are deliberately lined up because these are our models of extreme helium stars, and these are some other models, and these tracks come down here to where these green triangles are, and we think these OHE stars, the third group of stars in our group, these are stars that have oxygen. They've got helium, but they have nitrogen on the surfaces. They may have a little bit of carbon as well, but it's the nitrogen richness which is a bit of a giveaway. So, and all of these stars will turn around the corner and eventually become Dio white dwarfs, and that purple box there is the Dio white dwarf in our sample. And so that's really a summary of where we are. We have 4 different types of stars or super hot stars in our sample. The OH stars are probably the first time, the first attempt to become a white dwarf. The PG1159 stars, the ones that tried to become a white dwarf and failed, they became zombie stars for a while. The OHE stars probably started off life as a double star system, merged, and are now making their final approach to the white dwarf sequence. And the hot Dio white dwarfs could be descended from the PG1159 stars or maybe the OHE stars. And so there we are. We're back to here. But why were they? What was really the bottom line of this story? We've seen all of these types of stars before, but amongst our sample was the hottest Dio white dwarf. the hottest OH star without a nebula, and the hottest GW Virginis star. And we could have thrown all of those in the bin. Nearly did. So that was really a very, very satisfying study. What's next? Well, what's next is that we're going to use the incredible power of Gaia to focus and to find new candidates for our survey. And what Gaia can do, just in summary, is that Gaia tells us the parallax. It tells us how far away a star is. It tells us how bright it appears, and it can tell us what the color of the star is. And with those three things, we can determine the luminosity of the star, the temperature of the star, and the radius of the star. What we can't tell is what the surface chemistry is, and we can't tell you what the mass is. We need the spectrum to do that. So that's what we're going to try to do. And the second interesting thing is that when we do that, and we look at hot subdwarfs, we see lots of hot subdwarfs on this banana shape here. These are the normal, uninteresting ones. The red one, the green ones are the ones that I've observed in the survey. And the most interesting ones are all up here. These have radii, they're bigger than normal subdwarfs. And we can actually find these we can find where these interesting ones are using Gaia. These are the red squares. All of these points are based entirely on Gaia data. So this is our sample. This is the way we are going to select our sample to find really interesting objects in the next survey. And this is my final slide. I'm just now doing the phase 2 preparations, preparing the observing blocks for the next part of this. So phase 1 of our survey, we observed 100 stars up to about 2020, and those are published. Phase 2, we're just making the final sets of observations at the moment. We've observed over 200 subdwarfs, and those are the numbers of hours we've had. And we've just been allocated 92 hours in the next semester of solstice time. And over the next 3 semesters, we plan to observe 400 of these hot subdwarfs. And I hope that we'll find at least another 8 super hot zombie stars within that sample, but we'll see. So thank you very much for your time.
It's absolutely fascinating. Stars is just increasing bizarrely, isn't it? Isn't it really? And can I just ask you a very simple question to start off with? Why do you not blow the dust off those mirrors with like a blower?
You don't go anywhere near an optical surface with anything.
Okay.
Never, ever.
You really think they would have nice clean air wafting, the stuff?
Well, you do. Well, they do, and there are louvers on the sides of the dome, and there's lots of technology in the ventilation systems, because you're in a building that's sitting in the sunshine, in the South African sunshine in the daytime, and in the cold night time. So the temperature differences during the course of the night are huge. You can probably see in that picture, there's the top of the building in there. So it's an entire air conditioning plant in there with vast pipes that run underground into the building to do that. And you see all of those side windows open. That's to ensure ventilation through the building. Dome seeing is the biggest enemy of the astronomer, and dome seeing is where the seeing from a large telescope is determined by the column of air between you and what you're looking at. and essentially by the turbulence within that column of air. And dome seeing is where that turbulence is local, and you can avoid that, or you can reduce that by ventilating the dome correctly. Ideally, you want cold air to be coming in.
Okay, you're obviously trying to keep the mirrors at a very constant temperature as well, so as your
yes. So
distortions minimized.
I mean that's a horrendous problem. That tower thing is that tower thing up there is situated at the centre of curvature of the main mirror, and when you've got a multi-mirror telescope, you've got to basically each mirror is a segment of the sphere, and they've all got to be perfectly aligned, and there are actuators behind them and edge sensors all around the edge of them. And I occasionally see in the logs mirrors gone off again, or realigning the mirror. So they've got to take the telescope back and start again and realign everything.
Yeah, I know what you mean, Sam. We've got a 16-inch telescope, and David has to call me in it all the time. So, right? Any questions? Any good questions?
Sam, thank you. Very interesting. How far are these zombie stars? I mean, are they all in our Milky Way? Or
Yes.
Yeah.
Yes.
Okay.
Yeah. I should know the answer to this. They'll all be around the kiloparsec range. They're not. Then most of them are not as far as the galactic center, but they're not local. They're mostly not nearby. There'll be some that are nearby, but 1 to 2 kiloparsecs is probably the minimum.
I was going to ask a similar question. Simon, you showed a picture of the globular cluster, and I presume some of these fellows live inside the globular clusters, do they? Because there's supposed to be, well, there's planetary nebula inside globular clusters.
Yep. It's a good question. It's a question that's got lots of probably really long answers, because to some extent the evidence is that the hot subdwarfs in globular clusters aren't the same as the hot subdwarfs in the field, but that doesn't make a lot of sense, except that we know that binary stars have more difficulty surviving in globular clusters than they do outside. So the connection between binary stars producing hot subdwarfs and so on, it's not so clear. But really, the question ought to be: should we find any of these super hot stars in globular clusters? And I don't know the answer to that. And the reasons for that, I think, are, as you probably will be aware, that making observations of faint stars in globular clusters is incredibly difficult. And although the intrinsic brightness, the overall brightness of these super hot stars is huge, 10,000 solar luminosities, it's all in the ultraviolet. These are really ultraviolet stars. The amount of light they emit in the visible light. So when we take a photograph of a globular cluster, we're not going to see them. We only see these things once we start taking pictures in the ultraviolet sky. So a telescope like GALEX, the GALEX survey telescope, has been a great finder of hot stars. It's bright in the ultraviolet, you get to see it. But GALEX hasn't got huge resolution, spatial resolution, so it's not been great in globular clusters for finding these things. So really, the Space Telescope has done some work on imaging, ultraviolet imaging in globular clusters, and that's really interesting. But I'm not aware of any of the really hot stars. So.
Okay.
Simon, I must say, when I saw that headline, I knew it would be a fascinating lecture, so I'm really glad I asked you. It's been a fascinating talk, so much new stuff there. I'm just thinking, with those very, very high temperatures, are you getting the creation of elements much heavier than iron? You know, we think of supernovae and neutron star mergers and so on now are sort of postulated as the sources of a lot of the heavy elements, but with those high temperatures, are you also getting element creation?
Again, two answers to that is that the surface temperatures are not high enough in themselves to be responsible for nucleosynthesis. But the reason that we can get some very interesting nucleosynthesis is that when we have this very late thermal pulse, or the double white dwarf mergers, during that process or during the flash, the temperatures are high, and we're looking at material that is not normally mixed. So we're seeing in the post-merger objects, we're actually seeing oxygen 18 in huge amounts, nearly as much oxygen 18 as there is oxygen 60. You don't see that in any other circumstance. In the final flush objects, like saccharized object, we're seeing a lot of fresh S-process elements. So barium, zirconium, and so on. And whether this is a principal region for it, I'm not sure. No, I don't think they're a dominant source of any of those elements, but they do produce stars that are exotic in having very high individual abundances of.
And when you mentioned one of your slides there, one of the very first variable stars, observed Arc Corona Borealis. What then would be the source of the sudden dimmings of about 8 magnitudes? You sort of thought to be due to the production of dust in the atmosphere, but that would hardly apply in a white dwarf, would it?
Well, it's not a white dwarf when it's an Arc Corona. When it's an Arc Corona Borealis.
But I thought you were classing that our subdwarf anyway.
It's not. No, I'm not classifying them as subdwarfs. No. My diagrams do tend to cover most of the HR diagram, or at least the hydrogen deficient HR diagram.
But are they very high temperature?
The Arc Corona does. No.
I see.
When they expand, after the merger, the star expands to become a yellow giant.
Right. Okay.
With a surface temperature between 5,000 and 7,000 Kelvin.
Right.
And it's so big and so carbon rich, and it pulsates and lots of other stuff.
Yeah.
That I think the pulsations and shocks driven by the pulsations produce shock cooling, makes carbon condense into form dust, and these dust clouds then are ejected.
Right. I just understood the thought on the diagram with very high temperature.
Yeah, sorry, there's a lot in there.
Okay, no problem. My fault.
And mine.
Any other questions? Very conscious of the time here, Simon. I want you to get this train. Just one last one, maybe I could squeeze in. Just there seems to be this family now of white dwarfs. Is there a base white dwarf which won't do any of these strange things?
Oh yeah.
Is there an end point, like, you know?
Yes, most white dwarfs will not do anything.
Not do any of this. Yeah.
Yes, the final flash will occur in a very small number of white dwarfs. We think that the reason, or the conditions are set when the star leaves the asymptotic giant branch. The asymptotic giant branch star is going through a series of what are known as thermal pulses. It has a helium burning shell, but the helium burning shell is not a constant energy source. It switches on, and off, and then there's long periods of time in between where it settles back down, and hydrogen takes over. And then the helium shell goes and goes on. And it's when the phase in that cycle, when the star leaves the AGB and contracts, seems to determine whether or not it'll experience that last conjunctly as a white dwarf rather than on the HEP. So it's they are rare. You know they're rare because you haven't heard of them before.
Until tonight.
Until tonight.
Okay, well, listen, ladies and gentlemen, that's fascinating. One of the things which I certainly got was you almost scrap the results, and then all of a sudden you find a new family of stars, which is fascinating, really enjoyable. Simon, thanks very much indeed. Ladies and gentlemen, can I ask you?